Hello, science fans! Today we're going to talk about something truly brilliant. I mean that literally. We're talking about the sun. The sun is a giant star, a massive ball of hot gas, located about 93 million miles away from us. Every single day, it sends an incredible amount of energy, hurtling through space in the form of light and heat. This energy, which we call solar energy, is what makes life on Earth possible. It helps plants grow, it warms our planet, and it drives our weather systems. For a very long time, we've simply enjoyed the sunshine. But now, we're learning how to capture its power in a big way. So, how do we catch that sunlight and turn it into something we can use, like electricity to power our video games or charge our phones? The answer is a nifty little device called a solar cell, or a photovoltaic cell if you want to get fancy. Think of a solar cell as a tiny, flat engine that runs on light. When sunlight hits the surface of a solar cell, it knocks tiny particles called electrons loose from their atoms. These moving electrons create an electric current. It's an amazing process, converting light directly into electricity without any moving parts, noise, or pollution. It's pure, clean energy, straight from our nearest star. Now you might be asking, Bill, why is this so important? Well, consider this. For many years, we've been getting most of our energy by burning fossil fuels like coal, oil, and natural gas. While these fuels have powered our world, they also release gases into the atmosphere that are changing our climate. This is a huge problem for our planet. Solar energy, on the other hand, is a renewable resource. The sun isn't going to run out of fuel for about another 5 billion years. That means we have a clean, reliable, and super abundant source of power just waiting for us to use it. Harnessing it is key to building a cleaner, healthier future for everyone. The need for this shift to clean energy is more urgent than ever. As our world's population grows, so does our demand for electricity. We need more power for our homes, our schools, our hospitals, and our industries. If we continue to meet this demand with old, polluting technologies, we'll only make our climate problems worse. By embracing solar power, we can build a sustainable energy system that powers our future without harming our planet. It's a way to keep the lights on for generations to come, while also taking care of our one and only home, Earth. It's not just a cool idea, it's a necessary one. To build a solar cell, you need the right ingredients. The star of the show is a very special element called silicon. Silicon is the second most abundant element in the Earth's crust, right after oxygen. You can find it in sand and quartz. But we can't just use any old sand from the beach. For solar cells, we need extremely pure, high-grade silicon. This is called polysilicon, and it looks like a collection of shiny gray crystals. This ultra-pure silicon is the semiconductor material that forms the very heart of the solar cell. It's what allows those electrons to get excited and start moving when sunlight strikes. Besides our main ingredient, silicon, we need a few other materials to make the magic happen. To get the electrons to flow in the right direction and create a useful current, we have to dope the silicon. This doesn't mean giving it drugs. It means we add tiny, controlled amounts of other elements. We typically use phosphorus to create a negative layer or N-type, which has extra electrons. Then we use boron to create a positive layer or P-type, which has holes where electrons are missing. The boundary between these two layers, called the p-n junction, is where the electrical field is created, and it's the most critical part of the whole cell. The first major step in the factory is to take that pure polysilicon and melt it down in a very hot furnace. The molten silicon is then carefully grown into a large cylindrical crystal called an ingot. Imagine a giant, perfectly formed gray crayon. This process has to be done very slowly and under precise conditions to ensure the crystal structure is perfect. Once the ingot has cooled down, it's time for a haircut. The round ingot is squared off and then sliced into incredibly thin pieces using a special saw with diamond-tipped wires. These ultra-thin slices are called wafers, and they are the foundation upon which each solar cell is built. Before we can start building the cell, these wafers need to be squeaky clean. I mean, cleaner than clean. Any dust, oil, or microscopic impurity on the surface could ruin the cell's efficiency. So, the wafers go through a series of chemical baths to wash away any damage from the sawing process and to remove any contaminants. After their bath, the wafers are textured. Their smooth, shiny surface is etched to create a rough, pyramid-like structure. This might seem strange, but it's a clever trick. The rough surface helps trap more light by reducing reflection, ensuring that as much sunlight as possible is absorbed by the silicon instead of bouncing off. Now that our silicon wafers are clean and textured, It's time to create that all-important PN junction. This is done through a process called diffusion. The wafers are loaded into another super hot furnace, but this time a gas containing phosphorus is pumped in. At these high temperatures, the phosphorus atoms seep into the very top layer of the silicon wafer. This process creates the thin, electron-rich N-type layer on the surface of the P-type wafer. We now have our PN junction, the electronic heart of the solar cell that will direct the flow of electricity when the sun shines on it. It's a delicate, high-temperature dance of atoms. After diffusion, we have another important coating to apply. Even with a textured surface, some sunlight will still reflect away. To minimize this, we add an anti-reflective coating. This is typically a very thin layer of silicon nitride, which has a distinct blue or dark purple color. This is why most solar panels you see on rooftops have that characteristic deep blue hue. This coating is applied using a process called plasma-enhanced chemical vapor deposition, or PCVD. It sounds complicated, but it's basically a way to deposit a super thin, uniform film onto the wafer that helps it drink in even more sunlight. Every photon counts. With the core structure complete, our cell needs a way to collect all those moving electrons and send them out as usable electricity. This is where metallization comes in. Using a technique similar to screen printing a t-shirt, a pattern of thin metallic lines is printed onto the front and back of the cell. The front uses a grid of very fine silver lines to collect the current without blocking too much sunlight. The back is typically coated with a full layer of aluminum. These metal contacts act like a highway system for the electrons, gathering them up and guiding them out of the cell so they can do useful work for us. Finally, each cell is ready for a test drive. The completed cells are placed into a machine called a sun simulator. This machine flashes a powerful light, mimicking perfect bright sunlight onto the cell for a fraction of a second. Sensors measure the cell's performance, checking its voltage, current, and overall efficiency. This is a critical quality control step. Cells that meet the high standards move on to the next stage of production. Those that don't are sorted out. This ensures that only the best performing cells will end up in the final solar panel, ready to generate clean power for years to come. A single solar cell doesn't produce very much electricity on its own. To generate a useful amount of power, we have to string many of them together. This is where we go from making a solar cell to building a solar panel, also known as a solar module. In the factory, robotic arms carefully arrange the individual cells into a grid, typically with 60 or 72 cells per panel. Thin metal ribbons, or bus bars, are then soldered to the front of one cell and the back of the next, connecting them all in a series. This is just like putting batteries in a flashlight end to end. Connecting them in a series adds up their voltage to create more power. Once the cells are all wired together, this delicate matrix needs protection from the elements. A solar panel has to be tough enough to withstand rain, snow, hail, and decades of intense sunshine. The string of cells is carefully placed between a durable sheet of tempered glass on the front and a protective plastic backsheet. Then, layers of a clear adhesive called EVA, or ethylene vinyl acetate, are added. The whole sandwich is then put into a laminator, which uses heat and pressure to melt the EVA and seal everything together into a single weatherproof unit. Finally, an aluminum frame is added for structural strength, and a junction box is attached to the back to provide the electrical connections. Safety and precision are everything inside a solar cell factory. The manufacturing process involves high temperatures, strong chemicals, and very delicate materials. Workers often wear full-body bunny suits, gloves, and masks to protect both themselves from the chemicals and the solar cells from any dust or particles from them. A single speck of dust can ruin a cell. The air inside the factory is heavily filtered to create clean room environments. Quality control is constant, with automated systems and human inspectors checking the product at every single stage, from the raw silicon ingot to the final framed panel. This ensures every panel is safe, reliable, and efficient. The solar cell industry is growing faster than ever, and that's fantastic news for our planet. Every solar panel that rolls off an assembly line is a step toward a cleaner energy future. As technology improves, scientists and engineers are constantly finding ways to make solar cells more efficient, cheaper to produce, and more durable. This means solar power is becoming one of the most affordable and accessible sources of electricity in the world. From giant solar farms in the desert to panels on our own rooftops, the work being done in these factories is directly helping us fight climate change and build a brighter, more sustainable world. Now that's what I call brilliant science.